Hey, today I want to talk about section 3.1, maximum and minimum values. So this is our line. I want to talk about the definition of maximum and minimum values. Second one, how to find maximum and minimum values geometrically and algebraically. The next two, I know let you know extreme value theorem and Fermat theorem. I can talk about definition of critical numbers. The last one is the closed interval method for finding absolute maximum, absolute minimum. Definition of maximum and minimum values. This is definition. The T is the domain of F. The C is a number in the domain D. So first definition, F has an absolute maximum at C. The definition is like this. F of C is greater than or equal to F of X for all X in D. F has an absolute minimum at C if F of C is less than or equal to F of X for all X in D. Third one, F has a local maximum at C if F of C is greater than or equal to F of X when X is near C. F has a local minimum at C if F of C is less than or equal to F of X when X is near C. The last one, if F of C is a maximum or minimum, then F of C is called an extreme value. What's like extreme value? Maximum or minimum. So we call extreme value. This is like a definition. So we can replace absolute by global. What does it mean? We can change this one to the like this. So we can change it. This one is like global maximum. Global maximum, same. So this is global minimum. Global minimum. We can change it like this. So we can replace local by relative. Since the local maximum is exactly same to relative maximum. So local minimum, same. Relative minimum. You can change it like this. So I will explain. Here, absolute maximum. This is like a graph. So we have graph is like this. This point is like a C. What's that? This is absolute maximum, is it right? So F of C is absolute maximum in this case? Yes or no? Yeah, this is absolute maximum because you can choose any point X, find function value. So this point is F of X. This the highest point is exactly F of C. So F of C is the greater than or to equal to F of X. We call absolute maximum. The absolute minimum, similar. The graph is like this. This point is absolute minimum or local minimum. We can only locally. You can call like this. So this point is the relatively lowest point, is right? So this is local minimum. I'm going to give the one example here. What is the answer? We have the A, B, C, D, E is given. Find absolute maximum. At which point of X has absolute maximum? Is it T? Is it right, T? Is it T? Yeah, it's right. Highest point. This is exactly highest point, absolute maximum. Was it like x value for which f is absolute minimum? Yeah, lowest point. So this point is here exactly the lowest point. The f of a is lowest point, absolute minimum. So another one, local maximum value at x. So was it like x values? Local maximum values? T, yes. T is local maximum value. Yeah, P is also the local maximum value because this point D, you can think about locally. You can cut the like this, only think about this portion. So this point is locally highest point, is right? Locally highest point, local maximum. Same. This point cut like this, locally highest point. The locally highest point will be. So we have D and B. What's E? No. So that's it. This is P and D. What's the local minimum values? E and C is right. Yep. This is this point. We can cut like this. Only think about this portion. Only locally lowest point. Yes. This one same. Look, we have to think about this portion. The locally lowest point at C. How about A? How about A? Yes. Yes. Really be careful. So if you don't find local maximum, local minimum, we have trouble. Here, in this point, you can cut like this. From this portion, yes, locally lowest point, but what is x values less than a here? So we don't have a function value. No function value. No function values on the left-hand side. So what does it mean? So we cannot compare f of a with function value on the left-hand side. We cannot compare. So no, we don't have local minimum at endpoint. The next one, CE. The A is just absolute maximum. Only endpoint is here. So no, we don't have a local minimum, local maximum. We always non-negative. We can compare. Negative, it's good. But one important thing is that endpoint one. This is the same. This is not local maximum because the what does mean the near, you can cut here the like this. This portion locally has point, but what happens right hand side? The right hand side, we don't have a function value. We cannot compare. We cannot compare. So this endpoint with function value on the right hand side. So we don't have a local maximum minimum. You're right. Endpoint, we cannot compare anything. So we don't have a local maximum. We don't have a local minimum at endpoint. You have to always exclude endpoints for finding local maximum, local minimum. But absolute maximum, absolute minimum are possible at endpoint. So here, in order to find absolute maximum, absolute minimum, include endpoint. So like this one. We have absolute minimum. In order to find local maximum, local minimum, exclude endpoint. We don't have it. We don't have it. The extreme value, local maximum or local minimum at endpoint, impossible. Always exclude endpoints. It's good. This is idea. The next This is an example. The first one, we think about here, -1 to here, 13. -1 to 13. This point is like 13 here. So -1 to 13. The domain is -1 to 13. So like this. This is closed interval. So like this. What's x value? Absolute maximum. So which one is highest point? It's right. What do you think, the other guys? Is right? Yes. This is highest point. You can define, compare. This is exactly highest point. The other all function values below f of 11. So 11 has absolute maximum. What's absolute minimum? Yes, lowest point. You can include end point, the lowest point. So here, -1. The next, I know find local maximum, local minimum. We think about local maximum at x, find local minimum at x. Here, the first one was like a zero, local maximum or local minimum. How about zero? Local minimum, local maximum. What's that? Answer is neither. Because you can cut locally. It's cut the locally, the like this. What's that? From here, this is not highest point. We have highest point here, right hand side. This is not lowest point here. We have the low values on the left hand side. This is nothing. Nothing. So not local maximum, not local minimum. How about one? Local maximum, local minimum, or neither? What is the answer? One. Local maximum. Yep. Con like this. Point compare with left hand side, highest point. Compare with right hand side, highest point. This is local maximum. One. How about two? Local minimum. Is it right? Yes. You can cut like this. So 2 has, this is a function value 2. You can compare with left-hand side. Yes, lowest point. Right-hand side. Yes, lowest point. This is local minimum at 2. What's it 3? Neither. Maximum. Local maximum. Yes, local maximum. You can cut locally. Like this. What's f over 3? F over 3 is function value here. So you can compare with left-hand side. So this is function value f over 3 is greater than left-hand side, the greater than right-hand side. Yes, this is local maximum at 3. How about 4? Neither? Yeah, neither. Not minimum, because f over 4 exists one. What's f over 4? F over 4 is this one. This f over 4. You can cut locally. Cut locally. Cut locally. This point is not highest point here. This is higher, the left-hand side higher than this point, not lowest point, right-hand side, the nothing, the neither, the neither. How about 5? Yeah, neither, because we don't have a function value. So function value does not exist. No, no, neither. the not maximum, because function value does not exist. Function value f of 5 does not exist. So we don't have a function value, non-maximum. It's non-maximum. What's 6? Neither, same reason. Function value f of 6 does not exist. So we don't have a local maximum. We don't have a local minimum, neither. How about 7? Local maximum, is it right? Local maximum? What do you think? Local maximum? Yeah, this is a local maximum. You can call locally. The function value f of 7 is this closed dot. You can compare with left-hand side. This point is higher. The right-hand side, higher. Yes, local maximum at 7. How about 8? Local minimum, yes. Call like this. This is a function value closed dot. Compare with the left-hand side, lower. Compare with the right-hand side, lower. This is local minimum at A. How about 9? Neither? The neither? Yeah, neither. Because here, call like this. Function value is this one. Not lowest point. The low value is on the left-hand side. Not highest point. The right-hand side is greater than point. The neither. Right? How about 10? What's 10? Yes, local minimum. You're right. Local minimum. Call like this. This corner is lowest point. Compare with left-hand side, right-hand side. This is the lowest point. Local minimum. How about 11? Local maximum or minimum? Yeah, global maximum is true. We already have it here. But my question is local maximum, only local minimum. Yeah, absolute maximum is true. So local maximum or local minimum? Or neither. Local maximum. Here, locally highest point. This is low values, left-hand side. Right-hand side is low values. So this is local maximum at 11. What's 12? Yes, local maximum. Call like this, locally. The function value f of 12 is the greater than right-hand side, greater than left-hand side, left-hand side, the right-hand side. So this is local maximum at 12. That's it. This is the whole idea. Endpoint, so don't think about local maximum, local minimum. You have to exclude endpoint for finding local maximum, local minimum. Okay, good. Thank you, guys. So like this. So here, f of x equals x squared plus 1. So what is the graph? Graph is like this. This is like going up. This is going up. So like this. So do we have absolute maximum? So do we have absolute maximum? No. Graph is going up, going up, going to the positive infinity. We don't have a finite number. No. We have absolute minimum. Yeah, absolute minimum is 1. So what's like maximum minimum value? Always y value here. The y value is 1. So answer is 1. So another one is f of 0. So like this. This is absolute minimum. Local maximum, same. We don't have it. Local minimum here. Locally lowest point, this one. Yes, 1, f of 0. Like this. We can restrict the domain. -1 to 2. This is like stop. This is stop. Like this. Do we have absolute maximum? Do we have absolute maximum? Yes, highest point. So you cannot find absolute maximum, absolute minimum. You have to include endpoint. Include endpoint. 5. It's a 5, like f of 2 is absolute maximum. We have it. Yep, include. Yeah, just no local. We have to exclude the local. Yes. Absolute minimum. Yes, 1 here. This is y value is 1. The function value is f of 0. So like this. We have a local maximum. Yes, in this case, no. You're right. No, because we have to exclude endpoints. Local minimum. Yeah, 1 here. Locally, lowest point. 1, the same. The similar one, domain change. The graph is like this. Here, like this. What is absolute maximum? No. No. Absolute maximum is, as I said before, what's that? Y value. Here. Y value 5. The all function values below y equals 5. It doesn't matter. We have 2x value has same y value, not a problem. This 5 is absolute maximum. It doesn't matter. So here, f of 2, f of negative 2. Yeah, not a problem. Only one y value. It's good. This is absolute maximum. Absolute maximum. Absolute minimum. Yeah, same. 1 here. Local maximum. Yeah, no. You're right. Local minimum. Yes, 1. The local minimum 1. Yeah, so like this. F of x equals cosine of x. You can sketch the graph. Graphs like this. Do we have absolute maximum? Yes. What is absolute maximum? Yeah, y value. What's your y value? 2. Yeah, 1, 1. Yes, this is 1. We have, this is 1 here. All function values below y equals 1. This one is absolute maximum is 1. Absolute minimum is, yeah, this point, absolute minimum. Y value is -1. Yes. Local maximum is, what's the local maximum? Yes. Here, this value, y value is 1. Here, y value is 1. Here, y value is 1. Yes, 1. What's the local minimum? -1. You're right. Locally lowest point, -1. Locally lowest point, -1. -1. Just y value. Y value. So we have infinity many x values, but y value is just -1 and 1. So like this. Graph is like this one. So going up, this is going down. Do you have absolute maximum? What do you think, other guys? Do you have absolute maximum? No? This is not 6. The real domain, this is going up. So going up, this is going down. So not 6. Yeah, infinite. Infinite, like this one. The maximum minimum value is always finite number. The graph is going up, like a positive infinity going down, negative infinity. In this case, we don't have a maximum, we don't have a minimum. No. Absolute minimum is, what's absolute minimum? The same, not minus infinity. The minus infinity is not a finite number. Absolute minimum does not exist. So what's the absolute maximum, absolute minimum, local maximum, local minimum? Just a finite number. We have infinity, not absolute maximum, not local maximum. The minus infinity, not absolute minimum, not local minimum, but nothing. So similarly, local maximum, no. Local minimum, no. We don't have anything in this case. F for x equal to 5. What's the absolute maximum? 5 is right? Yes, 5. So what's the definition of absolute maximum? F of c is always greater than y equal to any function value f of x. What's f of c? 5. What's f of x? 5. Yes, always satisfies definition. Absolute minimum is, what's absolute minimum? Yes, 5 again. What's the definition of absolute minimum? Same. F of c is less than y equal to f of x. F of c is absolute minimum. So what's f of c? 5. What's f of x? 5. Yes, satisfies inequality. This is 5. Local maximum, 5. Local minimum, 5. Same reason, the same reason. So this is always 5. So next, so we think about this one. What condition of a function f guarantee that f has an absolute maximum, absolute minimum? What kind of conditions? So here, do we have absolute maximum? So do we have absolute maximum in this graph? Yes. Which one? What's x value? Yes, C. This is absolute maximum. Do we have absolute minimum? Yeah, D. This is the lowest point, highest point. Next one. So do we have absolute maximum? Yes, we have it. Absolute minimum here. So we have it. Do we have absolute maximum? Absolute maximum? Do we have absolute maximum in this graph? No. So we don't have a function value. This is open. We don't have a function value. No. Absolute minimum is 2. So we know function f is discontinuous at 1. So do we have absolute maximum? No. Graph is going to positive infinity. This is nothing. No absolute maximum. No absolute minimum. Domain is open interval. Right? So what kind of condition do we need? Here. What's that? Graph is well connected. Yes. Continuous. The first condition is function is continuous. The another condition was domain. Domain is closed interval A, B. Here, closed interval A, B is domain. So domain is open interval, sometimes does not exist. So we have 2 conditions. Function f is continuous. First condition on closed interval A, B. We need these conditions for finding absolute maximum, absolute minimum. The extreme value theorem and the Fermat theorem. Here, extreme value theorem. The function f is continuous on a closed interval AB. Then f has an absolute maximum like f of c, absolute minimum f of d. The some numbers c and d in the closed interval AB. So that's it. This is called extreme value theorem. So what kind of conditions guarantee that function f has absolute maximum, absolute minimum? Continuous, closed interval AB. We need these two conditions. One more question. How to find the extreme value? The extreme value is maximum or minimum. So I'm going to give one idea. So f of c is local maximum, is right? Local maximum. What's f of d? F of d is local minimum. Here, this is local maximum. This is local minimum. Local minimum. What is f prime of c? What's f prime of c? 0. Is right? 0. Yes. Slope of tangent line is 0. F prime of d is same result. Slope of tangent line is 0. So we have this one. So we have Fermat theorem. Function f has here local maximum and local minimum, and f prime of c exists. What does it mean? Function f is differentiable. So what happens? F prime of c equal to 0. Prime of c equal to 0. We call Fermat theorem. So what is it like converse one? So we think about this one. The converse one is like this. This statement is true or false. What do you think? This statement is true or false? If f prime of c equal to 0, then f has a local maximum or a local minimum. So what do you think? Yes? It's true? True? How about other guys? It's true? What do you think? It's true? Like the last example, yeah, the last one, seems like true, but unfortunately false. Here, counter example is f of x equals x cubed. This one. F prime of x is 3x squared, right? X cubed prime 3x squared. So f prime of 0 is 3 times 0 squared is 0. So this 0 is like c. F prime of c equal to 0. So what's that? Here we have tangent line. Tangent line is like this. This is not local maximum, not local minimum. No, we don't have it, right? This is the first. So if f prime of c does not exist, then f does not have a local extreme value. The extreme value is maximum or minimum. So what do you think? This statement is true or false? True? True? It's true? This is also false. We have counterexample is f of x equals absolute value of x. Like this. What's that? Local minimum at x equal to 0. But what's f prime of 0? Does not exist because corner. This is corner. F prime of 0 does not exist. So, but f has a local minimum at 0. The statement is false. So really be careful. Only this one is true. If f has a local maximum, local minimum at c, f prime c exists, then f prime c equal to 0. Only this case. So the other case is no. No. So from the previous example, here we have a local maximum, local minimum. What kind of property do we have? F prime of c equal to 0, is right? So like this. Last case is, so we have local minimum, f prime of c does not exist. So what does it mean? We have this result. From Fermat's theorem and the remarks, we know f may have a local maximum or local minimum at c if f prime of c equal to 0 or f prime of c does not exist. Is right? So in this case, is graph is like this: local maximum f prime of c is 0. In this case, we have corner. Local minimum f prime c does not exist. We have two possible cases for finding local maximum, local minimum. So we need one definition of this kind of point for finding local maximum, local minimum. So this one, a critical number of f is c, such that c is in the domain of f, either f prime of c equal to 0 or f prime of c does not exist. So this is definition of critical number. So why do you need this critical number? Because we may have a local maximum, local minimum at the critical number. This is the reason. Yes, we need to evaluate the critical number. Yes, we need these kind of things. I will give some examples to you here. Find the critical numbers of f. F of x equals the square root of x times 1 minus root x. Second one, f of x equals 1 over the square root of 1 minus x squared. Third one, f of x equals absolute value of x squared minus 4. So what's like a definition? First, you can calculate f prime of x. Next, calculate f prime of c equal to 0 or does not exist. The last one is, you can check. This number c is in the domain or not. This is a whole procedure for finding critical number. The first one, f of x equals the square root of 1 minus x. I want to distribute the square root of x to the first and the second one. So we have root x minus the square root of x times the square root of x is x. Change it to the, so like this. Next, you calculate derivative. F prime of x is here. First one, you can use power rule. What's the power rule? X to the power n prime. So we have n times x to the n minus 1. You can use it. So 1/2 is down, x to the power 1/2 minus 1 minus. So x prime is, what's x prime? What's x prime? The answer is, 1. So like this. And simplify. 1 over 2, x to the minus 1/2. Minus 1. I can change it to the positive exponent. X to the minus 1/2 is 1 over x to the 1/2. Minus 1. This is the same to 1 over 2 times. X to the 1/2 is square root of x. Minus the 1 is 1 over 1. I can change it to the only one fraction. You multiply top and bottom by the common denominator 2 times root x. This one. So we have 1 minus the 1 times 2 root x is 2 square root of x over common denominator 2 square root of x. This is whole idea for finding f prime of x. This is the first one. So like this. So we have it. The next, what's like the definition of a critical number? You can check either one. F prime of c equal to 0 or f prime of c does not exist. F prime of c equal to 0 is, you can calculate f prime of x. You can replace, this is x here. F prime of x equal to 0. So just this one equal to 0. So which one equal to 0? Numerator or denominator? Which one? top one or bottom one? So which one equal to 0? This whole thing is 0. The top one equal to 0 or bottom one equal to 0. Which one? Here. Which one? Bottom one? So we think about it. Top one? Yeah. What is 0 over 3? What is 0 over 3? 0. What is 3 over 0? Does not exist. What is 0 over 0? So we don't have this kind of things. So here, only numerator equal to 0. So in this case, what's that? Numerator equal to 0. F prime of x does not exist, like bottom one equal to 0. The bottom one is the 2 times square root of x equal to 0. You can just solve this case. You add 2 root x from both sides. 1 equals 2 root x. So divide by 2. So this one is 1 over 2 equals square root of x. Last one, square both sides. X equals 1 over 4 with one number. Here, the divided by 2, the root x equal to 0. What is x? What is x? The square root of x equal to 0. What is x? Yes, 0. Because the square root of x equal to 0, the square both sides. Yes, inside always 0. Inside one is always 0. So we have like this. X equals 1 over 4, x is 0. So this is a critical number or not. What's the definition of critical number? Here. You're going back to previous one. So we calculate second case. Last one is check. So these numbers are in the domain or not. You can check in the domain or not. So substitute the 1 over 4 and 0 into original equation. Don't calculate, only plug. What's f of 1 over 4? The square root of 1 over 4, 1 minus square root of 1 over 4. So well-defined, well-defined. It's good. The 1 over 4 is in the domain. You plug 0, the 0. So we have f of 0 is square root of 0, 1 minus the square root of 0. Well-defined, well-defined. Yes, in the domain. So 1 over 4 and 0 are in the domain. What's the final answer? 1 over 4 and 0 are the critical numbers of f. So that's it. This is the whole idea. The whole idea for finding critical number. Second example, we use same method. Can use same method. So first one, before take derivative, I want to change this one to the radical form to exponential form. 1 minus x squared to the power 1/2. So change it to the negative exponent, like this. This is like the first step. The next, take derivative. You can use chain rule. Do you remember chain rule? This chain rule, the g of x to the power n prime. is like down the g of x to the power n minus 1 times g prime of x. This is like a chain rule, so we can use it. Minus 1 over 2 is log of n, down. Inner function 1 minus x squared to the power 1/2 minus 1 times inner function 1 minus x squared prime. So what's that? This is keep this one 1 minus x squared to the power negative 3 over 2 times 1 prime is 0, negative x squared prime is negative 2x. This one. So what's that? You can change a little bit. This is same to the negative 1 over 2 times, change to the positive exponent, 1 over the 1 minus x squared to the power 3 over 2 times negative 2x. What happens? 2 is crossed out. The minus 1 times minus 1 is positive x. We have x over 1 minus x squared to the power 3 over 2. So we have this result. That's right. So like this. Same. You can check either. So f prime of c equal to 0, f prime of c does not exist. So you can replace x, the same things. So this one is same to only numerator equal to 0. So we have x equal to 0. We have it. The second one, f prime of x does not exist, only denominator equal to 0. So we have 1 minus x squared to the power 3 of 2 equal to 0. So we have it. We can solve second one. Here, only inside one equal to 0. So it doesn't matter at any power, only inside one. 1 minus x squared equal to 0. You add x squared to the both sides. We have 1 equals x squared. You can take a square root. What is x? So what is x? So could you write your answer on the chatting board? What is x? Is 1? It's 1? 1? Plus minus 1. So because the x squared equals 1, you plug minus 1 into x, the minus 1 squared equals 1. So plug 1, 1 squared equals 1. So really be careful. So even power squared equals like number. So this is always this is like the one part of Fermat theorem. What's the Fermat theorem? So if f has local maximum, local minimum, what's that? F prime of x equal to 0. The one remark of Fermat theorem is that sometimes f prime of x does not exist. The f may have so local maximum or local minimum. Yes, some part of Fermat theorem. This is the main idea for critical number is the main thing is local maximum, local minimum. What does it mean? We may have a local maximum, local minimum at critical numbers. This is the reason that we can learn the critical numbers. Yes, this is one part. But the different topic. Yeah, but different topic. So we have the like this. You can check. You can substitute 0 into f of x. What's it like f of 0? F of 0 is 1 over the square root of 1 minus 0 square is 1 over 1. Yes, well defined. You plug plus minus 1 into f 1 over square root of 1 minus plus minus 1 square. The plus minus 1 square is exactly 1. It's 1 minus 1. What's that? 1 over 0. 1 over 0 is does not exist. The undefined. The undefined. So f of 0 is well defined. F of plus minus is undefined. What does it mean? We have only one critical number. So 0 is the critical number. This is like idea. Solve the problem. F of x equals x squared minus 4. We need to find critical number. So could you calculate f prime of x? You know, what's the absolute value of x squared minus 4 prime? Do you know? Yeah, this is like depending on like x squared minus 4. X squared minus 4 is positive. You can use the 2x. The x squared minus 4 is like negative 2x. We have two possible answers. You're right. Like this, but like sometimes not easy for finding f prime of x with absolute value sign. So what's like main idea for critical number? You can draw the graph. Do you know graph of this one? Y value is this one. This is so we have it. So you're right. So I can explain it later. So thanks. Here, so we have x-intercept negative 2 and 2 passing through this point. So what's like y-intercept? The y-intercept is minus 4 is y-intercept. So here, minus 4. Graph is like parabola. The parabola. This is y equals x squared minus 1. What is absolute value? This one. What is absolute value? Here. The negative 2 and 2, positive 1 doesn't change. Exactly. Doesn't change. Same things. So like this. What is negative 1? You have to reflect about x-axis going up. So like this. This is absolute value of x squared minus 4. So like this. So what happens? What's it like the definition of critical numbers? The critical number is the next one. This one equal to 0 or does not exist. Is it right? This is like a definition. So what does it mean? F prime of C equal to 0. We have horizontal tangent line at 0. At 0. So we know F prime of 0 equal to 0. We know F prime of C does not exist. We have cusp. Yeah, this is corner. Cusp. F prime of X does not exist. This is negative 2 and positive 2. We have F prime of negative 2 does not exist. F prime of negative 2, sorry, positive 2 does not exist. So we have it. So one more. 0 and plus minus 2 are in the domain? Yes. So this point on the graph, this point on the graph, this point on the graph. Yes, in the domain. Domain. So what does it mean? So we have 3 critical numbers, 0 and plus minus 2. Right? So this is the critical number. The next one. This is like the last part. How to find absolute maximum. This is not local maximum. The absolute maximum, absolute minimum. So this is like the last question. How to find the absolute maximum and the absolute minimum of a continuous function on a closed interval. So do you remember the extreme value theorem? Our previous theorem says the continuous function with closed interval has absolute maximum, absolute minimum. This one is, how can you find absolute maximum, absolute minimum? I'm going to give some idea from some examples like this. So we have absolute maximum at C, is right? This is absolute maximum. So what happens? What's F prime of C? F prime of C is 0. Here, horizontal, tangent line, what does it mean? C is critical number. Critical number. We have absolute minimum at B. The P is endpoint. Endpoint. The second one. So do we have absolute maximum? At which point? At which point we have absolute maximum? No? My graph's not good. Here, C. Absolute maximum. Yeah. Do we have absolute minimum? What's the X value? Absolute minimum. Yeah, T. Here, T. Lowest point, highest point. So like this. The C is critical number because this is corner. F prime of C does not exist and in the domain, the critical number. We have absolute minimum at D, same. This is corner, the not differentiable. F prime of D does not exist. D is in the domain, D is a critical number. The last case, do we have absolute maximum? Do we have absolute maximum? Yes. Not local maximum, absolute maximum. We don't have a local maximum, we don't have a local minimum, but absolute maximum is just the highest point in the domain. The A is absolute maximum. The P is absolute minimum and end point. You got it? So, at which point do we have absolute maximum, absolute minimum? Only two possibilities. What's that? Critical number, end point. Critical number, end point, end point. So we don't have it. We don't have more. Just critical number and end point. This is the idea. How can you find absolute maximum, absolute minimum? This is one important thing. So we have absolute maximum and absolute minimum at end point or critical number. Yes, you can find critical number and the end point, plug critical number and the points on the function. The biggest function value, greatest function value is absolute maximum. The smallest function value is absolute minimum. This is the whole idea. So we must have absolute maximum, minimum at critical number or end point. So how can you find? This is a method for finding absolute maximum, absolute minimum. We know that continuous function on a closed interval has absolute maximum and absolute minimum at critical numbers or endpoints. This is a closed interval method. To find the absolute maximum and minimum values of a continuous function f on a closed interval AB, step 1. Find the values of f at the critical numbers of f in open interval AB. Step 2. Find the values of f at the endpoints of the intervals. Step 3. The largest of the value from step 1 and step 2 is the absolute maximum. The smallest of these values is the absolute minimum value. That's it. We always follow 3 steps for finding absolute maximum, absolute minimum. This equation, find the absolute maximum and absolute minimum values of f of x equals x cubed negative 3x squared minus 9x plus 1 on the closed interval 0, 4. Step 1. So find critical number, take derivative, f prime of x. So what's that? X cubed prime is 3x squared minus 3 times x squared prime is 2x minus 9 times x prime is 1, 1 prime is 0. Exactly 3x squared negative 6x minus 9. I want to factor this one. I'll factor out 3. X squared negative 2x minus 3. You can factor more. X minus 3, x plus 1. The next, you calculate this one. Was it like a critical number? F prime of x equal to 0 or f prime of x does not exist. First one, f prime of x equal to 0 is this whole thing equal to 0. The 3 times x minus 3 times x plus 1 equal to 0. So you don't need a 3, just this one equal to 0 or x plus 1 equal to 0. So we have x equals 3 from the first part, second part minus 1. You're right. Yeah, thanks. So next one. F prime of x does not exist, impossible. So we don't have it. So because this is always well defined. So we don't have a denominator. So we don't have a denominator. So we don't have this one. We have 2 points. So which one is critical number? 3 minus 1 or both of them? What are the critical numbers? Minus 1 is a critical number. So both. So let me see. Was it like the first condition of a critical number? The C is in the domain. What's the domain? Domain is 0, 4. So ignore negative 1. Only choose 3 because 3 is between 0 and 4. 0 and 4. So we have one critical number 3. So like this. So like this. You calculate f of critical number. You plug 3 into f of x here. So we have 3 cubed minus 3 times 3 squared minus 9 times 3 plus 1. The 3 cubed is 27 minus 3 times 9 is 27 minus 27 plus 1. 27 is cancelled. The negative 27 plus 1 is negative 26. So we have this one. So like this. Next one, step 2. Find critical numbers at end point. Find f of 0. You plug 0 into here. 0 cubed, 3 times 0 squared, 9 times 0. So this is 0, 0, 0. Answer is 1. So we have it. The next, plug 4. Plug 4. 4 cubed, 3 times 4 squared, 9 times 4. You can use the like this. You calculate. So 4 cubed is 64. The 3 times 16 is 48. The 9 times 4 is negative 36 plus 1. And simplify. The 64 Negative 48, negative 36 is negative 84 plus 1. The 64 minus 84 is negative 20. Plus 1 is minus 19. So we have three values, negative 26, 1, and minus 19. So what's like step 3? So which one is absolute maximum? What's that? What is your answer? What is absolute maximum? Yes, 1. We have three function values. Absolute maximum is the greatest value. Greatest value is 1. Exactly f of 0. What's absolute minimum? Yeah, same. Three function values, the smallest value. The smallest value is negative 26. Negative 26. This is f of 3. This is a whole idea for finding the absolute maximum, absolute minimum. So this is all for today's lecture. Thank you for attending my live session. So if you have any question, could you write your question on the chatting board? I will answer your question. If you don't have any question, you can leave this live session. No question? Okay, good. You're welcome. Okay. Oh, yeah. Wait.